You know, to figure out where our planet is heading, sometimes you have to look back. Way, way back. Today we're going on a kind of scientific detective story, digging into Antarctica's ancient past to understand the very real future of our coastlines.
This right here, this is the question that keeps scientists and coastal planners up at night. I mean, it's not a matter of if the seas will rise, but when, and maybe more importantly, how fast. The stakes are just enormous, because locked away in the world's ice is a truly staggering amount of water. And this number, 5 meters, that's what we're talking about from just one particularly vulnerable part of the world, the West Antarctic Ice Sheet. 5 meters is over 16 feet. That's enough sea level rise to completely redraw the map of the world as we know it. So the big question is, what would it take to actually unleash it?
Well, to find that answer, scientists are basically becoming climate detectives. They're on the hunt for a good parallel, a time in Earth's history that kind of mirrors the warming we're causing today. And they've found one. It's like a 3-million-year-old ghost story that gives us a chilling preview of what could be coming our way.
So here's our game plan for this little investigation. First, we'll look at why Antarctica is basically a ticking clock. Then we're going to travel back in time to a period called the Pliocene to uncover that ghost story. We'll check out the amazing tools scientists use to read clues frozen in time, and then we'll get into a huge debate about how fast ice can really collapse. Finally, we'll bring it all back home and see what it means for our future.
All right, let's set the scene. We're going back 3 million years to a chapter in Earth's history called the Pliocene Warm Period. And this isn't just some random ancient history lesson. It's honestly one of the best examples we have for where our climate might be headed. To really get a handle on our present situation, climate scientists look at other warm times in Earth's past. The last interglacial, for example. That was a natural warm spell between ice ages about 130,000 years ago. But the Pliocene, from 3 million years ago, that's the one that's really compelling and for a very specific reason.
Okay, take a look at this. This table is so important. Look at that top row. Atmospheric CO2 levels back in the Pliocene were almost identical to where we are right now. But, and this is a huge but, look at the other rows. The world was way warmer and sea levels were up to 22 meters, that's 72 feet higher. It begs the question, if our CO2 is the same, why aren't our sea levels that high right now? The simple and kind of scary answer is that our giant ice sheets just haven't caught up to the warming yet. The Pliocene shows us where we're heading in the long run. The mystery is, where did all that extra water come from?
So to solve a mystery this big, scientists have to become detectives, piecing together clues from these incredible natural archives that have kept a perfect record of Earth's climate for millions of years.
And one of their absolute best tools is the ice core. By drilling deep, deep down into the ice sheets in Antarctica and Greenland, they can pull up these amazing cylinders of ice that hold a year-by-year, layer-by-layer record of the past.
It's a really beautiful and simple process when you think about it. As snow falls, it traps little bits of the atmosphere. Then over thousands of years, the weight of all the new snow on top squishes the older layers down into solid ice. And this is the magic part. It traps tiny, perfect bubbles of ancient air.
And this quote from Professor Mary Albert just nails why these ice cores are so incredible. She says, "These bubbles aren't a proxy or some kind of estimate. They are actual samples of the ancient air. So scientists can literally measure the exact amount of carbon dioxide that was in the atmosphere hundreds of thousands of years ago. It's like a time machine."
But of course, ice cores are just one piece of the puzzle. To really build a solid case, scientists look for other evidence to back it up. They look at things like carbonate crusts in coastal caves that act like bathtub ranks, marking the exact height of ancient seas. They study old shorelines that are still visible in the landscape. And they drill into the ocean floor, where the chemistry of tiny fossilized critters in the mud tells a story about past ocean temperatures and just how much ice was on the planet.
Okay, so what all this evidence is telling us is that our current CO2 levels have basically committed us to a world that looks a lot like the Pliocene, with much, much higher seas. The ice just hasn't gotten the memo yet. And that leads us to the most urgent and most debated question in all of climate science today. Once the melt really gets going, how fast can a massive ice sheet actually fall apart?
And this brings us right to the heart of the debate. On one side, you have a process called Marine Ice Sheet Instability, or MICI. You can think of this as a slow, steady melt from below, where warm ocean water just eats away at the ice over centuries. It's well understood, but it's pretty slow.
But on the other side is this newer and, frankly, more alarming theory, Marine Ice Cliff Instability, or MICI. This is a much more violent idea. The theory goes that if a protective ice shelf in front of a glacier shatters, you're left with these massive, unstable ice cliffs that just start to collapse under their own weight, and that could set off a runaway chain reaction. The key difference here is speed. MISI is a slow melt. MICI is a catastrophic collapse that could happen in decades, not thousands of years.
And this idea of a rapid collapse isn't just theoretical. Back in 2002, scientists watched, absolutely stunned, as the Larsen B ice shelf, a chunk of ice the size of Rhode Island, completely disintegrated in just over a month. And the moment that protective barrier was gone, the glaciers behind it sped up, flowing up to 8 times faster towards the ocean. It was just a shocking demonstration of how fast the system can change.
So this is the core of the debate, and it's science happening right now, in real time. The scientists who think MICI is a real threat say, look, the physics are simple. Ice cliffs taller than 90 meters just can't support their own weight. They point to things like hydrofracturing, where meltwater wedges cracks open, and real-world events like Larsen B as proof. But on the other side, critics point to some natural breaks in the system. They argue that as cliffs fall, the ice behind them stretches out and gets thinner, lowering the cliff height. The pile of fallen icebergs can create a sort of temporary dam that props up the ice face. It's a really intense but absolutely essential scientific argument.
So, let's bring all this ancient history and modern scientific debate back to the present. Why does an argument about ice that's millions of years old matter so much to us right now? Because of this number. Right now, 230 million people around the world live on land that is less than 1 meter above the high tide line. Suddenly, understanding how fast an ice sheet can collapse isn't some abstract exercise, is it? It's about the future of coastal communities everywhere.
And this is really where the rubber meets the road. This chart shows sea level projections for the end of this century. The bar on the left, the likely scenario, is mostly based on that slow, steady melt from MICI. But that bar on the right, the high-end worst-case scenario, that's what happens when you include the possibility of rapid collapse from MICI. This one debate over ice cliff physics effectively doubles the amount of sea level rise we might have to prepare for. And that difference, well, that's the future of entire cities.
So, at the end of the day, the Pliocene doesn't give us a perfect prediction, but it does give us a really stark warning. It shows us what is physically possible in a world with CO2 levels like ours. The detective story isn't over. Scientists are still working like crazy to figure out the speed. The past has shown us the destination. The science is now just trying to tell us how fast we're getting there. And that leaves all of us with a really critical question. Are we prepared to listen to the answer?